In handheld augmented reality, users look at an AR scene through a standard smartphone that they hold in their hand. Adding a mid-air pointing device like a pen to handheld AR creates a unique bimanual interaction that offers intriguing new opportunities. For example, you could use a system like this to design a virtual 3D model of a part right where its physical 3D printout will need to fit later. But handheld augmented reality creates perceptual difficulties. Many depth cues to correctly judge the distance of virtual objects in the scene are missing. There is no stereoscopic view in handheld AR, for example. This makes it hard to perform one of the most fundamental mid-air interactions, pointing at a three-dimensional point in space, for example, to start a pen stroke from the surface of the virtual cube here. Occlusion is a standard technique to provide depth cues. It helps judge the relative depth of objects in the scene. Our baseline technique to help locate the pen tip in the AR scene, therefore, renders it as a small sphere that disappears inside or behind virtual objects. We have designed 4 visualization techniques to improve on that baseline and to better support locating the mid-air pen in relation to virtual objects in the scene. The first technique, called Depth Ray, adds a label indicating the distance of the pen tip to the next object behind it. It builds on the fact that it is easier to assess the horizontal and vertical position of the pen than its depth position. The second technique, called Bubble, renders a bubble that gradually expands from the pen tip, highlighting all intersections with surfaces in the scene as it is expanding. The third technique, called Shadows, builds on the promising results of previous studies, casting shadows onto the ground to provide depth cues in virtual environments. But keeping ground surfaces and objects of interest in view at the same time is difficult in handheld AR. We alleviated this by implementing this technique using a virtual plane slightly below the viewport of the camera, which shows shadows of both the pen tip sphere and all other virtual objects. Our fourth technique, called Heat Map, shades all objects in the scene with a linear red-green gradient based on their distance to the pen tip. Very close surface areas are shown in blue. We compared the performance of these visualization techniques in scenes with solid and wireframe objects. We measured pointing precision, the time needed to move to the intended location, and when the users choose to turn on each visualization. We also asked our participants to rate all techniques on helpfulness, confidence, and comprehensibility, and to rank them based on preference. All techniques resulted in similar precision and task time, but the subjective ratings showed that users clearly favored the heat map technique, followed by the depth ray and shadow techniques. Our participants found the bubble hard to understand and use for determining the position of the mid-air pen. Our results provide first insights into what techniques to use to visualize a mid-air pen position in handheld AR systems.